I'm going to talk about two things this afternoon. First, in this first session, I'm going to talk about recent developments in SVAR, structural vector autoregressions. And then in the second session, I'm going to talk about dynamic stochastic general equilibrium models. So here's the outline of this first session. So I'm going to spend some time just going over the basics of vector autoregressions, which we all know, but I'm just going to establish notation and go over that so we're all on the same page. Talking about the identification problem, which is intrinsic to structural vector autoregressions, and then I'll talk about a number of procedures, some that are older procedures that have been around for a while, such as identification. Using short-run restrictions. Identification using long-run restrictions has been around for a while, but it continues to be an area of considerable interest. So I'll talk about that. And then there's a number of other areas that have developed more recently, where more recently means, say, the last 10 years, which includes sign restrictions, sign restrictions on impulse response functions, heteroscedasticity, DSGE priors, and then some miscellaneous other stuff, which is kind of application specific. So that's going to be the first, 2/3 of the talk, and then probably the last third I'm going to talk a little bit about inference. So the first part, essentially after the introduction, has to do with different schemes for identification, and then I'll talk about some issues of inference. I think there's been a lot of really interesting work in the last 5 or 10 years, let's say 10 years in this area, and it's been interesting for me to try to put this together. Okay, so I'm going to start at the basics, just a good place to start as the beginning. So the question that we're going to be interested in is, what's the effect on some surprise action, say the Fed raises the interest rates by a certain amount in an unexpected way. What's the effect of that surprise action on a variety of economic variables now and over the next several quarters? So that's what we would think of as a dynamic causal effect. And so a dynamic causal effect is, what's a causal effect? A causal effect is, I think, the way I like to think about it is in a statistical way. Imagine you have a randomized controlled experiment, and you assign some group in this randomized controlled experiment a drug and the other group a placebo. And if randomization is perfect, then that means that although there's heterogeneity across the different types of people, it's unrelated to who gets the drug and who doesn't get the drug. And on average, the difference between the two groups, at least in population, is going to give you an effect of the treatment in an idealized randomized controlled experiment. So we can think about there being analogous situation as a hypothetical way to start to be concrete about it, where you would have two parallel economies and everything is identical, and you randomly tell one board of governors to raise interest rates and the other board of governors is the control, and then you wait and you see what happens. And as long as those two economies are in some sense the same on random, or you have groups of economies where you've randomized the treatment among them, then you're going to be able to track out not just the immediate effect of this interest rate increase, but the effect over time. So it's a causal effect in a hypothetical experiment over time, which makes it a dynamic causal effect. That's not, so the FDA can do that with drug trials, and we don't have that flexibility. So we're going to have to use other techniques, or we're going to have to try to get at this in other ways. Okay, so that's what we're interested in, is this object here. The macro jargon for it is it's called an impulse response function. That's kind of dynamic causal effect is like all statisticians know kind of what that means. Impulse response function, that's just for us. That's our secret phrase. Okay. So the question is, how can we estimate this thing from macro data? Okay, well, I think it's useful to break this up into two large categories, or more precisely, one large and one small category. The large category is structural models, which is more or less what macroeconomists have been up to, or many macroeconomists have been up to for 60 years. And I'll talk about one category, category B, now, which is structural vector order regressions. I'll talk about the other category, more tightly parameterized models like DSGEs, in the next lecture. And then I am actually going to say a few words about natural experiments, because I think that's a useful way to think hypothetically about what we're up to, and about how we could try to look at identification out of the box in some of these problems. Okay, so here's the basic identification problem. So I've written out a two-variable system, but of course you can imagine this being a multiple, k variables or any amount of variables that you want. But 2 is all I had room for on the slide. So I've got a two-variable system, and this is a vector order regression. But there in blue is sort of the interesting and difficult part of the whole issue. So let's just stare at this for 1 second. What I'm interested in, we'll think about this as a linear structural macroeconomic model. So let's forget about worries about whether it's linear or nonlinear. Think about this as just a structural macroeconomic model, such as you might have learned about in graduate school in the old linear structural simultaneous equation systems days. Epsilon 1 and epsilon 2 are going to be these shocks, and we might be interested in looking at their effects. And to do that, we're going to need to be able to estimate these coefficients. Now, if epsilon 1 and epsilon 2 are serially uncorrelated, or more precisely martingale difference sequences, so that you can't predict them, then what that says is that all of these lagged variables don't really pose a problem. You'd be able to estimate the coefficients on lags. But the problem is, in this specification, is that I've got two variables here that are occurring contemporaneously. And so what's the deal? The deal is that y1 enters the y2 equation, so it affects y2, but at the same time y2 affects y1, and you're not going to be able to sort that out. And that's the identification problem in econometrics, which recent historical... that's the identification problem in econometrics. I was going to digress about a paper in the QJE in 1919, but I won't. By someone who was an assistant, not an assistant professor. He was an assistant to an assistant professor at Harvard at that. But anyway, that I won't digress. Okay. So the problem is that we can't just run OLS on this system. OLS, this is the classic problem. You got price and you got quantity, and you can't run price on quantity and quantity on price and expect to get anything. Somehow you've got to identify the system. So what are you going to do? All right. So obviously one way to think about this is IV, and we'll come back to that interpretation. But for now, we're going to think about this in terms of VARs. All right, so you can't actually estimate the coefficients in that what we'll call a structural VAR up here. So you can imagine that they really exist. This might really be the contemporaneous effect of interest rates on prices, and this might really be the contemporaneous feedback from prices to interest rates in the Fed reaction function, but we can't estimate them. So these are well-defined objects in some economic sense. We just can't figure them out from the data, and we'd like to be able to do that. All right, so the framework, one framework that's been very popular as a framework for thinking about this is vector order regressions. One thing you can identify is the reduced form of this system. Well, the reduced form of this system comes from solving out y1 and y2. If you solve out y1 and y2, then that gets rid of them in the other one's equation, and all you have is the regression or a projection of y on past values of y, and then some error term. Now, that error term is also going to be serially uncorrelated. It's going to be like that error term up there, but it's going to be kind of a solved-out version. So U's got some epsilon. U1 has some epsilon 1s and epsilon 2s, and U2 has some epsilon 1s and epsilon 2s. So it's going to be something that's correlated, and we're not going to know how that correlation structure is. At least it's not identified so far. But we can actually estimate these lag coefficients, and we can estimate the covariance matrix of the U's. Using lag operator notation, it's just represented as this A of L YT, where A of L is just this lag polynomial. And you can think of in a number of different ways. I'm going to think about them all of this not necessarily as being IID errors. You can think about that in a structural sense, or you can think about this as just being the population residual from projecting y. And this should be yt minus 1 given yt minus 2. This is projecting y. The population residual from projecting yt on yt minus 1. So this equation is correct. Okay. And then sigma u is the covariance matrix of these reduced form VAR errors. All right. So the trick is then going from the VAR, the reduced form VAR, which is observable, estimable, to the structural VAR. And so to do that, here's some notation and here's some assumptions. So first, I'm going to assume that it's conventional to assume that it's a finite order VAR. Now, as a practical matter, that certainly is convenient because it's not so easy to run VAR infinities. You can go through all of this theory, the identification certainly, without worrying about finite order lags. But as a practical matter, this is quite important. Next assumption, if what we can observe is the reduced form vector autoregression, but what we want to get at is the structural shocks and the structural vector autoregression, it better be the case that these errors U, which are the residuals in the reduced form vector autoregression, span the space of the structural shocks epsilon. Basically, you need to be able to go from the structural shocks to the reduced form errors and then back again. So R is going to have to be square and invertible. So you're going to be needing to go from one to the other. So I'll talk about that assumption later, but that's obviously an important part of this. Okay, and then finally, at least for the exposition that I'll be doing, you need to make some sort of assumption that these autoregressive coefficients are not going to be changing over time. Now, you can actually address that by explicitly modeling or analyzing whether or not some of these change over time. But for everything I'm going to be doing here, with one exception, we're going to model these as time invariant. All right. So with that, using this relationship between the structural shocks and the innovations, the reduced form innovations, it's possible for us to go from the structural vector autoregression from the reduced form autoregression to the structural autoregression simply by pre-multiplying both sides of the reduced form autoregression, the reduced form VAR, pre-multiplying them by R, and getting the structural vector autoregression. So this is then, in that notation, the structural vector autoregression, and then the final thing that we're interested in is what's the impulse response function. Well, if the epsilons are the structural errors, then the impulse response function is simply going to be the effect of those structural errors on y over time, and that's obtained from this moving average representation of the structural vector autoregression, where the moving average representation obtains by inverting the vector autoregressive coefficients matrices, and if you want to express it in terms of the original reduced form VAR and this rotation matrix R, this identification matrix R, you can do it that way. And then the impulse response that we were interested in, the effect of y, h periods hence, with respect to the structural shock or vector of structural shocks, is just this coefficient in the moving average representation of the structural VAR. So yeah, please. This is yeah.
How do you get R?
Oh well, how do you get R is what this entire literature is all about. So this is, it's like when you teach IV, where you start out saying assume you have Z such that. Okay, so I am assuming that we have R such that. All right, and by the way, I actually do relish questions. I think that the few questions that have come up in this have been great, and the questions afterwards have been really great. And so ask them. People will benefit. If they're too long, then I'll just say we have to talk about it later. Okay. All right. So this is just notation, and it's a little concise summary of what's going on. We've got the reduced form VAR, and we've got a structural VAR. And they are related to each other by this one magic matrix R. If you know R, you can compute all the impulse responses you want. Okay. There's an assumption that I'm going to make throughout, but it's worth just noting. It's made everywhere in this, almost everywhere in this literature, not quite everywhere, but almost everywhere, which is that the structural shocks are uncorrelated with each other. And to me, people, you could argue about that or not, but to me that actually makes a great deal of sense. If we're thinking of something as a structural shock, it really is, the Fed raising interest rates by a certain amount in some unexpected way that's unrelated to other things. If it's related to other things, then it's not the structural shock. So to me, that makes sense. But in any event, it's an identifying assumption that's used here and will be maintained throughout. Okay. One other tool in vector autoregressions is something called variance decompositions. Okay, what a variance decomposition is actually a forecast error variance decomposition. It says if you're forecasting output growth 4 quarters from now, how much of your forecast error on average is going to be explained by shock 1 or shock 2 or shock 3. So if it turns out that monetary policy shocks explain a small fraction of forecast error variances, say 8 quarters ahead, you might say monetary policy isn't very important in that sense. I'm not going to talk about variance decompositions at all in this talk. I'm going to focus on inference for impulse response functions, which is actually the effect of the shock out in the future, which is in a number of ways, I think, a more interesting question. But in any event, once you have these impulse response functions and the shock variances, you can do these calculations to get variance decomps. Okay. So this magic matrix R. So there's actually 2 ways to think about identification, and one of them is what's come up, which is somehow if we have a device or a tool that will help us identify R, then we're in business. And that's the way that much of this literature goes. But I think it's useful to say that there's another way that's really equivalent to think about identification, which in some ways is more intuitive rather than just this matrix. And the other way to think about identification is suppose for some reason, let's just suppose that you could estimate one of these shocks, one of these structural shocks. So since we're interested in the effect of monetary policy, let's call R an interest rate. And I'm sorry about all of the R's here. Little r and big R are different objects. R sub t is like a Fed funds rate, okay? And so we'll call this the monetary policy shock. So that's the amount that the Fed funds rate went up at after some meeting of the FOMC in an unexpected way. Right? So that's their monetary policy shock. Well, let's just suppose, hypothetically, that in the minutes of the FOMC, they're into transparency, or increasingly into. That's probably an overstatement. They are starting to think about issues related to transparency. And let's suppose they went all the way and they published epsilon TR. This meeting's epsilon TR is, and they wrote down a number, 22 basis points. Well, that'd be great. We'd be done, right? We'd be in business because we would just need epsilon TR by definition is uncorrelated with everything else. And so what that would be saying, that of course, if you think about the release, would be bizarre. It'd be saying, based on all of the information in the economy, we should be raising interest rates by 25 basis points, but you know what? We're not going to do it. And so then at the end they say epsilon T sub R, epsilon TR equals minus 0.25. And so that's what it would be. And so if they publish that, you could then, in fact, just run this regression. So you could just run a regression of y on your history from the minutes of epsilon TR. And the nice thing about it is that it is, by construction, uncorrelated with everything else in the economy. So there's 2 ways to think about identification. One is this sort of algebra way, this R, but the other is if I had this epsilon TR, I'd be in business. Actually, these are equivalent. If you had all of the epsilons, you could figure out the R's. If you had the R's, you could figure out the epsilons. You can do it either way, but I like this intuition. Okay? Okay. let me talk about this natural experiment approach before we get into VAR particulars. I actually think it's useful when we're thinking about identification to go back and think about instrumental variables and ways that we could identify that are not narrowly within all of the endogenous variables in the system. So what if you had, let's just imagine, here we go. Suppose there exists a z, okay? Suppose there exists a z such that z is correlated with interest rate movements. Z is correlated with epsilon tr, all right? But it's uncorrelated with uncorrelated with all of the other shocks in the economy. So here I've written it down. Let me be this precise. Suppose you have some instrumental variable z, and it's not one of the variables in y. It's just like something else. It's an IV. It's not in the system. And it's going to be exogenous in the sense that it's uncorrelated with all of the other structural shocks in the system, except it's correlated with unexpected movements in interest rates. Well, that's what you need for an instrument. And if you had that, let's just suppose that you had that. Suppose you had that thing, then you could actually estimate this system by IV. So here's the algebra of how you can, or here's the argument of how you can estimate this thing by IV. It's on the next page, but I'll just do this. Suppose that you actually had this instrument Z. All right. Well, Z is by construction uncorrelated with the error term in the innovation equation for X. But it's by assumption correlated with the innovation in the interest rate. So you can use it as an instrument in this equation, or actually, if you've got k equations or k-1 equations, you can use it in an instrument in each one of them. That means you can estimate this coefficient. This is a vector, by the way, so this is k-1 by k-1 times k by k-1 by 1. So you can estimate this vector of coefficients. Well, since you know this or can estimate it, you can subtract off this bit and you're left with a residual. Well, now that residual is up to a rotation, the structural shocks up to a rotation in X. Well, those structural shocks of X are going to be correlated with the innovation of X, so you can use those as instruments in this equation for this k-1 included endogenous regressors. Subtract off that term, and there you have it. Okay, there you have it. You've got up to scale, which is irrelevant. You've got the structural shock for the structural policy shock. So if you had an instrument, you only need one, that satisfies these two conditions, you've actually been able to identify not everything. You can't identify all of these X shocks, but you can identify the shock that you're interested in, which is a policy shock. So I'm chair of the department, and I was in a meeting with the provost and the other day. And he's asking me what I do. And so we're talking about monetary policy a little bit. And I'm saying how it's so hard to figure out what the effect of monetary policy is on the economy. And he looks at me like I'm an idiot, And then to make matters worse, I said, well, what you really would need is you would need the Fed to run some experiments. I'll tell you what the perfect thing would be. The perfect thing would be, which is that they have a meeting and then they say that we're going to raise interest rates by 25 basis points, but then the person who's transcribing it types it wrong and they make it 55 basis points. So they raise it by 55 basis points, and then we have this, but then we know that in retrospect. So we have this surprise of 30 basis points. So I'm telling this to the provost, and the provost just looks at me. So he's, I'm sure that sort of the budget for the department just went down by about 50,000 in that one meeting. He said that really wouldn't be a good thing. Okay. Romer and Romer, that wasn't the device Romer and Romer used. I think that the Romer and Romer idea of bringing outside information by reading the minutes and trying to see what might be surprise information and what might not be is brilliant, okay? I just think that's such an interesting idea, and it hasn't been used very much in this literature. Whether one agrees with the particulars of the reading and the particulars of the definition or not, it's a very interesting idea to try to bring external information in this natural experiment way to help identify these problems, which I have to say, there are, hundreds of papers in the literature on VARs, and it still is a hard problem that nobody really agrees on. So they've got a series of interesting things that I think is a really interesting approach that merits more work. Okay, so this just says that. All right, so now SVARs. SVARs, instead of bringing in, so it really is an analogy. There is that analogy there in natural experiments, which is we're trying to bring information that's not in the system, something new, something exogenous, to try to identify something that's going on in an endogenous system. SVAR approach takes a different perspective, which is we're going to use some sort of economic theory, formal or informal, to identify that R or to identify the shocks, and use that then as the mechanism for identifying the impulse response functions. All right, so the first papers were these three that are listed up there. And so the basic idea, one way to think about it, I think the easiest way to think about it mechanically, not economically, but mechanically, of what's going on is that the only thing you've got in SVARs here is this equation, all right? So the structural shocks are related to the reduced form innovations by this linear system where R is a square matrix that in general doesn't have any restrictions on it. What that says is that if you compute the covariances from that, then it says that you've got this equation. Well, this is a k by k matrix, so it looks like you might have k squared equations, but these matrices are symmetric, so half of it's useless. So you only have k times k plus 1 divided by 2, which is the diagonal element in below, to be separate equations. So you've got k times k plus 1 divided by 2 distinct equations. You might have the number of parameters you would have is k squared. So it looks like it would be more than k squared if sigma epsilon is diagonal and then R is full. So that would mean you'd have k in sigma epsilon and k squared in R. But one of them is just a normalization. So you could arbitrarily set sigma epsilon to be the identity matrix, and that's just going to get rid of a normalization problem. How big? What are the units for a structural shock, which is not important. You can do the impulse responses in any units you want. So you're going to have k squared unknowns. And you have k times k plus 1 divided by 2 equations, so you're going to need at least k times k minus 1 divided by 2 restrictions on R to get this thing to work if you want to identify all of R. All right, so in the case that k equals 2, that only means that you need one restriction, but more generally you're going to need more than that. And in the case of k equals 2, if you just go right up here, you can just see what's going on. Suppose, just for the sake of argument, that we had some theory that says that y2 actually doesn't appear in the y1 equation. Then you've got an exclusion restriction, and it says that you can use you could estimate this. And one way you could think about that is as IV estimation, where you would take epsilon 1t, which you would be able to compute, because if this isn't here, you then just subtract off these bits, which you can get. You've got epsilon 1t, and you could use that as an instrument for the included endogenous regressor y1t here. It's uncorrelated with the error term because it's a structural shock, and you'd be able to identify the system. So that's just simultaneous equations theory. Okay. There's rank conditions which will come up, but I'm not going to really focus on those because that's case specific. All right. You could also approach this by partial identification. I think that's implicit in what I just have already said, where if I knew the epsilon TRs, if I knew the structural monetary policy shocks, then I'd be able to identify the system. And you can make that whole argument here in terms of only identifying one row of this R matrix. And it's the same thing as what I was saying before in ideas. Okay, so there's this idea called invertibility. Okay, so here's my one word on invertibility, which is Blaschke. So there's this What does invertibility mean? All right, so there was this assumption that, let me write this up since this is an important equation. Okay, so there's this assumption that R ut equals epsilon t. So what this is that I can take linear combinations of u and I can get epsilon. Another way to say that is that the space of innovations has to span the space of structural shocks. These innovations are the residual from the population regression of y on its past. The space of the innovation spans the space of y contemporaneously. That is, you can use past values of the innovations to construct y, or past values of y and innovations to construct y. And that's what's meant. So the term that's used for that is that these are fundamental. And so fundamental is kind of a funny term because it's not fundamental in any economic sense. It's fundamental in the statistics sense, which is that you can take those innovations, these u's, and you can build up through the moving average representation. You can just build up the y's. These are the u's that are recovered from projecting y in its past. These are the wall decompositionary u's. The requirement is that the wall decompositionary u's span the space of the epsilons. And that's an assumption that's sometimes called invertibility. And you can write down models in which this is actually not true. That is, the structural shocks are not spanned by the u's. And you can kind of think that that's, in some sense, that seems like it's got to be really obvious, really. If you suppose you're looking at a two-variable VAR, and you think there's 7 structural shocks in the economy, how can you possibly get all 7 out of these 2? What you're going to get is some mishmash of them, and sort of the formal way to say that mishmash is to say Blaschke factors and go over, and then there's a bunch of papers. And I'm not going to go over that anymore. Except to say that the usual response to this problem is to make sure that there's enough variables in your VAR that you're convinced that you really do span the space of structural shocks. So I find that to be a useful response, but there's a fair amount of you could pursue this if you want. You can talk with Mark about this during the break. Okay. All right, so let me talk. What I'm going to do now is talk a little bit about some of the, here's this early promise of SVARs, which is certainly true. I'm going to talk about some of the challenges to them that were brought up in the 90s, some of the new ideas about how to tackle identification, and then a number of issues on inference, including some tools. Okay, so some comments. This is going to have a bit of a flavor for a while, for the next half hour of a survey. I don't know. I'm not going to be going through a whole lot of algebra. I'm just going to be sort of summarizing, giving you my take on what the major developments have been in the literature. And there's a number of good background references here. Lutkapol's reference is not really on any of the economics, but it has all of the math of VARs that you would ever want to know. Okay, so let me start out with short-run identification restrictions. So this is the benchmark way, the original way that VARs were identified. One way to think about, what is this equation doing? This equation here says that there's a relationship in the short run, that is to say, a relationship within the month in which these shocks are occurring between the u's and the epsilons, and maybe we can use timing type information to identify. And so the most familiar of these timing type restrictions is the one that I've written down right here, and this is just taken from the Handbook of Econometrics chapter, Handbook of Macroeconomics chapter by Cristiano, Eichenbaum, and Evans. And it's imagining that you can partition the variables according to a group of slow-moving variables, your policy variable of interest, and then a group of fast variables. And the slow-moving variables are going to be taken such that the monetary policy shocks don't affect the slow-moving variables within the period. So this is the classic story that, say, prices don't respond to interest rate movements within a month, within the month in which they occur. If that's the case, then the effect of interest rate innovations or interest rate changes on innovations in the slow-moving variables is zero. And then there's some fast-moving variables which are in this structure going to respond within the month to interest rate changes. And so those might be asset prices, so for example. And then the Fed, what the Fed is assumed to do, well, it's assumed to have this structural innovation, but the Fed is also assumed to look at innovations or equivalently structural shocks that it observes happening in the real economy, and using that information in the period, it then sets interest rates. So that's the benchmark timing story. That story has sort of I guess that was the main story that was developed in the SVAR literature in the late 80s. Not the only one, but maybe the primary one. It's related to essentially being able to do a Cholesky decomposition or something like a Cholesky decomposition of the covariance matrix to identify the R's. It generated quite a bit of criticism. There's a paper by Rudebush that summarizes a lot of that criticism. And I think that probably most of the members of this audience are pretty familiar with those critiques. I think one of the a variety of critiques. One of them is that the VAR doesn't the monetary policy rule that's implicit in there really doesn't come close to recognizing the amount of information that the Fed takes into account in setting monetary policy. The monetary policy shocks that are estimated here don't match match ones from the futures market. So there's a variety of critiques that were made. I'm not going to go into that, but I think those are pretty well articulated in that paper. Okay. So essentially, one way to look at the VAR literature for the last 10 years is as a series of responses to these problematic and challenging critiques of this initial cut of short-run timing restrictions. And so one way that this has been handled is by looking at high frequency data to try to estimate monetary policy shocks. I think the cleanest example of that, I think there's some reasons why in the end it wasn't very successful, but I like the idea is super clean, which is a paper in the AER by Cochran and Piazzesi. And so what they did is they went and they looked at daily Eurodata data, and on the days that there were monetary policy announcements, they looked at the change pre-announcement and post-announcement of the Eurodata interest rate. They then added those up for the month. So some months there were zero, right? If the open market committee doesn't meet and there were no announced changes, some months they're zero, other months they added them up, and you can imagine if there's some time that they made intermeeting changes, and some months there might be two. They added those up, and they created a monthly series of interest rate surprises, which is the change before the announcement, after the announcement of the euro-dollar rate, and that constituted their monthly measure of epsilon TR. And then the thing that's great about that, at least conceptually, is if they're right, if that really is what epsilon TR is, then they're back in this setting right here. And all they need to do is just run the regression of y on those epsilon TRs, and they're done. And so they do. I mean, there's some problems. You can read the paper. I'm not going to critique the particulars. They get very strange responses, and I think it has to do with particulars of how it was constructed. But I like the idea is a nice idea. It's very clean. There's some other papers that have much more sophisticated approaches to trying to back this out from the term structure of interest rates pre and post announcement, and then using that to match impulse response functions. I'm going to come back to the Faust, Swanson, and Wright paper, which is actually quite sophisticated in its econometrics at the end. Bernanke and Kuttner also have a paper that essentially is using these short, very super high-frequency data to estimate monetary policy shocks effects, and then use that to identify the VAR. So I think that's one promising approach. Okay, so let me talk about long-run restrictions. So I'm just going through a variety of different approaches to identify VAR. Is there any questions at this point? Okay. So another approach to identify VARs is through long-run restrictions, which is something that was developed back in the late 1980s. And so the methodology there is to say that the long-run effect of one variable on some other variables is going to be zero. One shock on some of the specific variables is going to be zero. One way to think about, there's a couple of ways to think about this. In those coefficients, those autoregressive coefficients, if you have a shock, the long-run effect is going to be related to the sum of those moving average coefficients. It just sort of, you can see, if you think about that moving average in your head, it just kind of piles up over time. So D of 1 is the sum of those moving average coefficients. You can do that, make that statement a little more formal by doing the Beveridge-Nelson decomposition, which you may or may not recall. You should recall. It's a great little decomposition, and it decomposes y into a summation of y, something with a random walk, into a permanent component and a transitory component. And the weighting on the permanent component is this D of 1. It's the sum of the effect. So if one of these epsilons has no long-run effect on the y, then that element of D of 1 would be 0. All right, so that's one way to motivate these. All right, so what this is going to entail is a long-run restriction is going to entail putting a 0 in D of 1, or equivalently a 0 in A of 1. It depends how you set up the particulars. All right, so if you recall before, what the identification in this short-run restriction was running off of R sigma u R prime is equal to sigma epsilon. Well, in the long-run setup, what you're interested in instead is you're interested in the long-run effect. Well, the long-run effect is going to be something like A of 1. And so A of 1 times ut is equal to D of 1 times epsilon t. And so the restriction that you're now going to be interested in is going to be a sort of a long-term relationship between these, and that's going to be summarized in the spectral density matrix at frequency 0. So the spectral density matrix at frequency 0 basically says, A of 1 inverse. So the spectral density matrix at frequency 0 basically says that A of 1 inverse times sigma u times A of 1 inverse prime is equal to D of 1 times sigma epsilon times D of 1 prime. And so that D of 1 sigma epsilon D of 1 prime, there's an R hiding inside that. And so if I then make that explicit right here, I get this equation relating the long-term variance matrix or spectral density matrix at frequency 0 in the reduced form VAR to the spectral density matrix at frequency 0, the long-run variance matrix in the structural VAR. All right, so if I equate these two things, the spectral density matrix in principle is something that's identified. Remember, I can run the reduced form VAR, and I can get A of L, I can get sigma u, I can get A of L, so A of 1. Therefore, I can compute, or at least in population, know omega, which is the long-run variance matrix of the y's. So I can then equate that to this formula here, which involves the r's and sigma epsilon. Well, A of 1 itself is observable, so in principle, this is now my new matrix that I need to use for identification. So I've got k-squared elements here, k-squared elements here. They're redundant because it's a symmetric matrix, so it's exactly the same now mathematically as before, which is that I have k times k plus 1 divided by two equations here and I've got unknowns in this, and I've got unknowns in this, so I've got k-squared unknowns, and therefore I need a total of k times k minus 1 divided by 2 restrictions. So it's exactly the same logical structure as the identification using short-run restrictions, and the only difference is instead of using the short-run or one-step-ahead variance matrix, we're using the long-run variance matrix, which is this 2 pi times the spectral density matrix at frequency 0 type condition. That would impose a 0 in the spectral, in D of 1. Now, if I set the shock variance matrix to be the identity matrix, which I can always do that. That's just a normalization. So I'm going to set the shock identity matrix to be the shock variance matrix to be the identity matrix. Then this restriction or this equation from up here simplifies, and since this is omega and that's observable, I then get omega is equal to d of 1 prime. And that's with the sigma epsilon be the identity matrix. So now the problem here is going to be somehow solving for d of 1, and then using that solution to get r. If there's 0 restrictions, so here's the easy way to think about it. If there's 0 restrictions and this is lower triangular, then that just says that d of 1 is the Cholesky factorization of omega. We can observe omega, so that says you compute d of 1 as the Cholesky factorization of omega, and from that you can then compute r. So that's the basic idea of estimation and identification for long-run neutrality. Okay, so this actually has quite a life. I mean, it goes back to some early work in the late 1980s, and it continues to be used. In part, I think it's been a center of a spirited debate about whether technology shocks lead to short-run decline in hours based on long-run restrictions. It's spirited and seemed to be almost endless debate, actually, I should say. So, and it's, I was on the 2 years ago. I was on the NSF panel on April 4th. So I was in Washington for a meeting, which happened to be when the macroeconomics annual meeting was in 2006. So I actually didn't attend the macroeconomics annual meeting. So in preparation for this talk, I went back and I looked at the discussion for the macro annual meeting. And some of you are probably there. It's really one of the more amazing. This is from NBER macro annuals published. It's one of the most amazing published discussions I've seen. It goes on for a while. This is about a paper by Cristiano Eichenbaum and Vigfuson, where they're talking about long-run restrictions and vector autoregressions and that sort of thing, and inference. And then there is a discussion by Pat Kehoe, who was actually also at the NSF panel with me, and he had scheduled 2 things on the same day, so it was given by Ellen McGrattan instead. I understand it made a big hit. And so here's the comments in the discussion, where Edward Prescott remarked that there are many exciting and interesting puzzles in macroeconomics on issues of great importance. In light of these facts, he felt it was unfortunate the discussion in this session seemed to be about how many angels can dance on the head of a pin. Prescott also remarked that the Lucas critique had taught economists that estimating structural VARs is inconsistent with dynamic economic theory. Sims responded that he felt it was great to get input on statistical methods from real business cycle theorists. Sims wondered why Chari, Kehoe, and McGrattan had turned their critique of Galli and Robinall into a critique in which they claimed that SVRs were no good in general. He wanted to be sure they were not trying to argue against all probability-based inference, because in his opinion, much of the discussion had that flavor. He suggested that if Chari, Kehoe, and McGrattan were going to conclude that SVRs were no good in general, then they should suggest some alternative methodology. Anyway, it would have been fun to have been there, I guess. So that's the spirited debate on long-run restrictions. Okay, so there actually, I actually think that some of this spirited debate has to do with problems of inference, and that in fact what's going on in these long-run restrictions is that there's some very delicate and difficult inferential problems, and they have to do with estimation of these long-run effects. I'll come back to this later, and then Mark will talk about this also tomorrow morning in the first bit when he talks about spectral density estimation at frequency 0. But there's been some quite interesting recent work, I think, that has interpreted this in an IV way, which links into what I was talking about yesterday. And so I'm going to come back, and I think that some of this recent work here can shed some light on this spirited debate. Okay. Identification by sign restrictions. Oh, man, I've got to speed up. All right. Sign restrictions. So sign restriction says the following. Suppose that you know a priori, or you have an opinion a priori that the impulse responses have to have a certain sign. The question is, how could you use that to identify a structural vector autoregression? And there's a number of different proposals that have been put forth. This is quite interesting. I'm going to just talk about one of them, which is Uhlig's 2005 method in a JME paper. And the basic idea there is, suppose you have some a priori theory that says that impulse response functions say have to be, the impulse response, a tightening of monetary policy cannot increase prices for the next 4 quarters, hypothetically. Suppose you wanted to make that assertion. Then how can you impose that? And that's actually pretty tricky to think about. And so this is a clever algorithm that Uhlig thought up, which is, first of all, to recognize that there's a fundamental identification problem. One way to think about the fundamental identification problem is that you can insert orthonormal matrices inside of R inverse, and you can get the same answer. So here's the algorithm, which is we're going to look at all possible R's. We want to map out all possible matrices R, and then only keep those matrices R that produce impulse responses with the signs that we like. Okay, so that's a well-defined problem, a well-defined mathematical problem that has a solution, and Harold has a clever solution to it. And he says, let's do this. First of all, we're just arbitrarily going to pick some R to work with for starters, and that's going to be a Cholesky decomposition. So he's going to take a Cholesky factorization here. Now that's not a structural R, but it's a useful device, because he's going to then insert inside that Cholesky factorization H prime, where H is an orthonormal matrix. So since it's orthonormal, H times H prime is the identity matrix, so this maintains the equality for all H's. But what that says is that if I could go through all possible H's, which is the space of orthonormal matrices, if I could just go through the whole space, that will generate by H prime RC inverse, or equivalently, if R equals H inverse RC, I will have generated the entire space of all of the R's. So one way to get all of the R's is to go through all of the H's. And all of these R's are going to be suitable factorizations by construction, because they're multiplying this Cholesky factorization. All right. So now I'm only going to want to keep some of those. So what I want to do is I want to go through the space of all of the R's, and then I only want to keep some of them, the ones that satisfy the restrictions. So the way I'm going to go through all the space of the R's is to go through all of the space of the H's. The way I'm going to go through all the spaces of the H's is actually just by sampling at random from the space of the H's. So if I just draw an H and I check it, either it works or it doesn't. So I draw another H, I check it, either it works or it doesn't. So I can go through all of the space of the H's, and I can find those H's that work. Work means they provide impulse responses that satisfy your sign restriction conditions. So that's the algorithm. That's his algorithm. Close to his algorithm. It's my interpretation of his algorithm, which is that you draw H from the space of orthonormal matrices, you compute R from this Cholesky factorization times the H inverse, you compute the impulse responses. You check to see whether the impulse responses satisfy the condition. And then Harold does this in a Bayesian way, and so he then evaluates all of these using prior. And the prior is going to be a combination of a prior on the A's and the reduced form matrices, which could be anything in particular, but it's convenient to use a conjugate prior, times this indicator function, which says I'm only going to keep a D of L if it meets my conditions. And then we integrate that over this space of orthonormal matrices, which is what we're drawing from using Monte Carlo. So that's the algorithm, and you keep the ones that you like, and then you compute, say, posterior reasoning using like Bayesian credible sets, which is essentially a posterior interval, a confidence interval based on a posterior distribution. Okay, so I want to make a couple of comments about this. It's very clever, and it certainly has some appeal. It raises a number of very interesting inferential questions. One of them is that this results in what's commonly called set identification. That is to say, there's not going to be a unique matrix R that satisfies these criteria because you said I want to have the first 4 quarters or the first 8 quarters of impulse responses for a specific impulse response to be positive. That's not going to uniquely identify your matrix R. It's only going to identify a family or a set of matrices R. And so what that means is that since you're only identifying a set of matrices R, you're only identifying a set of impulse responses. The impulse responses are only set identified. That is, another way to say it is that this restriction isn't going to distinguish among a whole family of impulse response functions that are going to satisfy this restriction. Inference for set identification is actually quite tricky. And I'll come back towards the end, I think. Oh, actually, no, I've got it now. Okay, so impulse for set identification is actually quite difficult. And so I'll talk about that in just one second. There's one other point that I do want to make, which is that there's an additional level of integration here that involves integration over this random draw from the space of orthonormal matrices. The space of orthonormal matrices. So since you're drawing at random from the space of orthonormal matrices, that means implicitly that you've got some prior distribution on the space of orthonormal matrices. That prior distribution on the space of orthonormal matrices is the one that's implied by your numerical algorithm for sampling for that space. An interesting question that I don't know the answer to, but I haven't seen explored in this literature, is whether or not the prior that's implicit by the algorithm that you use to sample over the space of orthonormal matrices actually has an effect on the resulting confidence sets, the Bayesian confidence sets. And I would imagine that it does, but I think that would be something to explore. It would be interesting to see. Okay, so let me tell you one thing about set identification. So set identification doesn't come up very much in macroeconomics, and I think this is one of the few places where it comes up in a serious way. When you estimate using the Uhlig algorithm the impulse responses that satisfy this condition, you are estimating a set of impulse responses. The set of impulse responses that you're estimating is not a confidence set. All right, what would a confidence set for a set be? A confidence set for a set would be a set-valued object that would contain the true set 95% of the time in repeated samples. When you compute your set of impulse responses, that's an estimate of the unidentified set. That's a point estimate, a set estimate of the unidentified set. It's not a confidence set. A confidence set would be another set that would contain the true set 95% of the time. Got it? When you suppose that you did this, you remember I've got all of these I've got all of these, in that set, I've got a whole ton of confidence bands from this random draw using the, right? So I've got a ton of I've got a ton of impulse response functions. Suppose out of those impulse response functions I took like the the inner 67%, and I plotted those, and I called that a 67% band. That wouldn't be a 67% band. That would be a band which would lie within your set that you're estimating. It's not a 67% band in any sense. It might be in some Bayesian sense that I don't understand, because I don't understand that very well. But it certainly isn't in any frequentist sense. It would actually be within the band, within the set, within the identified. The identified set is all of the ones. Faust and Swanson and Wright have a very nice paper where they go through this, not with this exact mechanism, but with another very closely related mechanism that gives them set identification using high-frequency data. This is a very nice paper. And this is their estimate of the identified set. I'm not going to go through how they did it. This is their estimate of the identified set. So this is a point estimate. So this is like plotting one impulse response in a fully identified system. This is the set that they estimate. They then do a Monte Carlo simulation where they then come up with a confidence set that would contain the identified set in 95% of realizations. Okay, so you with me? This is definitely tricky. We're not used to I'm not used to this. Okay, so this is their point estimate, and this is their confidence set. All right, so now, point estimate, but the point estimate's a set, and the confidence set is a set that contains sets. Now look, this is wild. Look at the scale. All right, so this is like 0 to minus 0.8. This is 0.5 to minus 1.5. This is 0.6. So the scale is actually really expanding on these. So these sets that contain sets, not surprisingly, are huge. It makes sense, right? This is the point estimate. So you want to have something that's going to contain this in 95% realizations. It's going to be really enormous. So the set that contains sets is really huge. So this has got to be an issue. I haven't seen this done, and yeah, there are experts in the audience on this procedure, and they might correct me, but I haven't seen this done for the sign restriction thing. It'd be very interesting to do it for the sign restriction thing. I think there's a lot of interesting inferential issues here. They're not ones that are impossible. The Faust-Swanson-Wright paper is a good step. Okay, identification from heteroscedasticity. This is cool. Okay? Suppose you have two regimes. Suppose that the economy got less volatile in 1984. Let's imagine. But suppose that the structural relationships didn't change. All right. So we're going to be precise. Suppose that we're going to have a model in which the structural shock variances decreased, not proportionally, but decreased, say in 1984, but that R matrix didn't change. So sigma epsilon is going to change, but R isn't. Well, that's terrific, because now I got a whole additional set of equations. All right, so I've got my equations before 1984, and I've got my equations after 1984, and it's the same R, but it's different shocks, so it's more equations. More equations, I can deal with more unknowns. In fact, I have k times k plus 2 over 2 equations here, and I've got another k times k plus 1 over 2 equations here. And if I add those together, I have k times k plus 1 equations, but I have k squared unknowns before 84, and now by changing the shock variances, I only have k more unknowns, so I have k times k plus 1 unknowns. You're done. That's so cool. So that's Riggerbone's 2003 paper. I really like this. I mean, I don't know if I like it in practice, but I like it in theory. And so here's the intuition that Riggerbone gives, which is somehow if you knew that the variances change, then you actually know that, like if you have one's supply and one's demand, and you know that the relative variances change, then if you know that the relative variances change, then you're going to sort of be able to deduce from that maybe things are lying more along a supply curve in one period than in the other. So that's another way to get some intuition. But I actually like the counting equations approach. There's a rank condition here, which I haven't gone through, but that's that's important. I mean, it certainly can't be the case. Suppose that all of the shocks, the structural shocks, increased by the same fraction. That's not going to identify it. You've got to actually have different equations. Right, so there's a rank condition that's involved. You could estimate the break date consistently. You can do it using conditional heteroscedasticity instead, like Arch. And so that's this Santana and Fiorenturini paper. I've never seen that implemented except there. A couple of things that I think one has to pay close attention to is, look, we said that in 1984 the structural variances changed, the structural shock variances changed, but nothing else in the economy changed. So you got it. That's the assumption. And it's also got to be the case that they have to change by enough that you'd actually, I said we got a whole other system of equations. Well, you only have another system of equations if they actually really change by enough. So if you don't have a big change, you're going to have a weak identification problem. It's not really going to solve anything. But it's kind of a cool idea. DSGE priors. I'm going fast because, well, fortunately, I have nothing to say about numbers 6 and 7, except that you should look at the literature, and I'll talk about this after our break. It's important. I don't mean to minimize its importance by being slow on it, by being quick on it. Rather, I'll come back to it when I talk about DSGEs. The next one, I'm going to be quick on it, which probably is to minimize its importance, which is to, in some very special cases, if you're working with multi-country models and you say that shocks transmit in proportion to like trade flows or trade shares or something like that, then you can get some identification out of that. And there's some literature. It is what it is. It's not like the greatest. Okay? I can say that because we have a paper on this. All right. Let me talk a little bit about inference. Okay, I'm going to talk about two main things in inference and two main things in inference. And the first one is going back to this long-run identification issue. And then the second is going to be about impulse response inference and confidence intervals. It won't be about confidence sets. It'll be the old-fashioned confidence. It won't be about confidence sets for sets. It'll be the old-fashioned idea of confidence intervals. Okay, so back to this spirited debate. The long-run identification structure, the long-run identification procedure led to an estimate of this magic matrix R that was obtained by doing a Cholesky factorization, assuming that we have, I'm working just for the sake of argument, that we have some reason to believe that there's a Cholesky factorization to the long-run impulse response matrix. So I'm just taking that at face value. I'm not going to argue with that. In the 2x2 case, it just says that, as in Blanchard-Qua, that aggregate demand doesn't have long-run effect on one of the variables. So I'm just going to take that at face value. I'm not going to argue with the economics of it. I'm going to just look at the statistics, the econometrics of that. All right. So we're doing a Cholesky factorization of the long-run variance matrix, which is 2 pi times the spectral density matrix at frequency 0. That is estimated by the long-run impulse response function of the VAR times the estimated covariance matrix of the innovations. And then I'm multiplying it again by a hat of 1. So that's our estimate of R. And, okay, so that's one way to think about it. I'm going to talk about it now as an IV estimator. And there's some really interesting work that was done 10 years ago, or I guess more when it was first done. It was published 10 years ago, which I think, as far as I can tell, must not have been very well understood. At least I didn't really appreciate it at the time. And it hasn't received too many cites until recently. But I'm going to go through it because I think it's very insightful. And so this is a paper by Pagan and Robertson. I mean, I was the editor on this paper, and I don't think I really understood it. So it's nice stuff. Okay, I think I understand it now. So So what this literature does is it sets up this long-run restriction problem as an IV problem. Okay, so we're going to do that. We're going to set up the long-run restriction problem as an IV problem. We'll do it in the two-variable case just because it's easier to look at. A long-run restriction on the impulse response, D1, 2. Suppose we have a long-run restriction of that being 0. All right, well, that's going to correspond to a long-run restriction on the coefficients in the 1, 2 part because the impulse response function is the inverse of the sum of the autoregressive coefficients in the structural VAR. And in a 2 by 2 case, this is just what the inverse is. And so this element is going to have to be 0. So it's basically the long-run impulse response 0 restriction corresponds to a 0 restriction on the sum of the coefficients in the structural VAR. So if we go back to I'm going to take advantage of that. What I'm going to do is I'm going to write just let me skip ahead one slide. So what I'm going to do is I'm going to take advantage of that expression that B1, 2 of 1 equals 0 to work out what the explicit restrictions are on this equation in the VAR. Remember, if you remember how I started saying that we needed some restriction, like an exclusion restriction, to deal with identification problems in the simultaneous equation system. It turns out that this long-run restriction provides another restriction that you can use for identification in an IV way. And so that's what I'm going to do. To do that, I'm going to use not the Beveridge-Nelson decomposition, which we saw before, but some version of the Beveridge-Nelson decomposition where I'm going to put C of 1 on the final lag. I'll leave this as an algebraic exercise for you, but you can rewrite, in some sense, a reverse Beveridge-Nelson decomposition where the long-run effect appears on the final value in the distributed lag rather than the first. So I'm going to take advantage of that, just by that, okay? Accept that. This is algebra that is correct. Okay? So what I'm now going to do is I'm going to rewrite this first equation, actually rewrite both of these equations, so that there's this long-run coefficient loading on y2 t minus p, the pth lag, and then everything else is in first differences. And then I don't care about these. These are lags, and so they're in the terminology. They're predetermined, so we can treat them as exogenous in the terminology of IV regression. So we don't need to worry about these. Anything with a lag we don't need to worry about in terms of identification. Here's the key point. Once I've done this rewriting so that one of these has the sum of the coefficients, I can now drop one of these by imposing that 0 restriction. The 0 restriction means that there's a variable that's now going to be excluded from one of these regressions. If there's a variable that's excluded, it means I can use it as an instrument. Okay? So there's my instrument. I've got an excluded variable, so I can use it as an instrument. And what am I instrumenting? Well, I'm instrumenting the contemporaneous value of the change in y2. All right, so if I look at that again, I'm going to be using this variable, which is going to be excluded from this equation, and I'm going to be using it as an instrument, since it's excluded, for the contemporaneous value of the change in y2. Well, I've got all these other lags in there, so that's equivalent to using yt minus 1, y2 t minus 1 as an instrument for delta y2. All right? So that's what it says right here, and then because all these lags appear, it's equivalent to using y2 t minus 1 as an instrument for delta y2t. All right? That's Pagan and Robertson and Cooley and Sart. Okay, do the algebra. It's correct. It's not mine. It's Cooley and those guys, Robertson, Pagan. Here's the point of those papers, which is if you think about what you're doing, you're saying, I'm going to use the lagged level of consumption as an instrument for consumption growth. I'm going to predict consumption growth using the lagged level of consumption. That's not going to work very well, right? That's going to be a bad predictor. of consumption growth. It depends. If it's a series that's not very serially correlated, it's going to be a pretty good instrument. But if it's a series that is highly serially correlated, consumption is about a random walk, so consumption growth is going to be unpredictable using lagged consumption. So in that example, that's an extreme case where it would be a really bad instrument. Maybe some other series would be not so bad. It depends on how serially correlated. In fact, if I do this back-of-the-envelope calculation where Y2 is an AR1, just to make this calculation simple, it's an AR1. So delta Y2 is related to Y2t minus 1 with the coefficient alpha minus 1. Well, this is my first stage, this is going to be a first stage regression in IV terminology, so I go back to my IV notation from yesterday. There's the concentration parameter, that's from yesterday. Well, pi is alpha minus 1, z is Y2t, sigma squared v is sigma squared epsilon 1. I plug everything in, I know what the variances are, I do the calculation. It's the variance of Y2t, alpha minus 1. There's a t floating around because that's z prime z. Sigma squared v is sigma squared epsilon 1. I remember what this thing is, right? This is sigma squared epsilon over 1 minus alpha squared. And I plug it in. There's the concentration parameter. Right? So I just computed the concentration parameter for this first stage regression in this simple example. Now, if alpha is small, it's like 1 over 1 times t, and this concentration parameter is going to be really big. And if alpha is big, like if it's, say, nearly 1, this is going to be really small. So you can take out a calculator or Excel or something, and you can compute this. And if alpha is big with 100 observations, it's going to be small. Mu squared of 2.6, right? That's bad, right? That's less than 10. Okay, so this was all worked out in a really nice paper that's coming out in the JBES by Gospodinov. And he actually works it out in a special case where alpha goes to 1 in a local to unity sense. And if you can do all of that in your head, what that means is that mu squared is, in his asymptotics, going to converge to a functional Brownian motion, and then you can get all of this distribution theory out. And it basically provides an explanation for why this really might be, or a mathematical way to say why this might be a weak instruments problem. Instead, that technology wasn't available to these papers back in 1998, but so what Pagan and Robinson did is they did a Monte Carlo simulation, and here's just a figure from their paper. And these coefficients, these B12 things, are like this. So they're like this object right here. So they're estimating they're this object right here. It's the one that's being estimated by IV. So it's the object that's being estimated by IV using these long-run exclusion restrictions. And this is just a Monte Carlo simulation that they did. And the thing that's kind of interesting about the Pagan-Robinson paper is they did 3 Monte Carlo simulations, and each one was calibrated to empirically estimated models. So they took 3 models from the VARs from the literature that were all like 6 variables or 4 variables, pretty substantial systems, not toy systems, that were published. And then they took the point estimates, and then they did a Monte Carlo simulation around those point estimates. And this is the result of the Monte Carlo simulation for these estimates of these coefficients that are needed to compute R. And you can see that these distributions are very far from a normal. A normal that comes close to fitting it is plotted in the background, but these are coefficients that actually have a very, very wide spread in the original units and far from a normal distribution. And so the implication there is that that's going to really complicate the situation for inference. Well, where does that take us in terms of this long-run restriction literature? I mean, to the extent that this weak instrument interpretation is valid, I think it does suggest a number of things that you would expect, which is that there would be a lot of sensitivity to the sample in these specifications. There'd be sensitivity to the lag length. Going from a VAR of 6 to 8 might make a big difference in terms of the estimate. There might be other sorts of delicacies that you would see. Certainly, if you do a Monte Carlo simulation, you would expect to see very non-standard behavior of these VAR coefficients. And not surprisingly, by the time you then invert them for impulse response functions, they're going to be all over the map in terms of their distribution. There's a couple of ideas that come out of that in terms of practical advice. One is to perform a Monte Carlo simulation or something like that to try to get a sense as to whether this might be going on in a particular application. There's another idea which is, I think, interesting in a paper here by Francis Oying and Roche, which says just don't use a long run or an infinite run restriction, change it to a finite run restriction, and use a different algorithm that's based on John Faust's 1998 paper. And that's, I think, interesting. I've only seen that one use of that, and I think it's an interesting approach. Okay. I think this is actually, despite the fact that it's been around for so long, an area that is not fully resolved, and it's a pretty interesting one. So let me make a final set of comments on impulse responses. Any questions at this point? Yeah.
Some of the debate that happened among the people in the macro annual thing had to do with the number of lags you put in the VAR. How does that kind of hook into whether this thing is?
So the question is part of the debate in the macro annual and in this Chari Kehoe McGrattan paper has to do with the number of lags in the VAR. And then how does that relate to this weak instrument interpretation? I guess the way I would say that is that one lesson from the weak instrument literature is that I don't have an algebra answer to that, but one overarching lesson is that seemingly minor little differences can make in weak instruments can result in very big differences in estimators, and it might well be the case that that's what's going on here. But I actually haven't seen that worked out in an algebra way, and that would be a good exercise to see if this explanation addresses that specific question that's hanging out there in the literature. There's an equivalency between what I'm talking about here and estimation of spectral densities at frequency zero. And we know that for estimation of spectral densities at frequency zero, that's a very delicate and a very difficult problem. Mark's going to talk about that tomorrow. And whether you add a few more lags, the thing is those coefficients might be small, but if they're adding to some things that are canceling already, they could make a big difference in in A of 1, and then you go and invert it, it could make a big difference in D of 1. So I think there's two ways to look at the lag problem. There's the weak instruments way, and then there's the spectral density matrix at frequency zero way. And I think at this point it's warnings. We don't have like a definitive answer. But it's not surprising. I'll tell you, from this perspective, it's not surprising that there would be these delicacies. Okay, confidence intervals for impulse response functions. So I'm going to end up going over by a few minutes, but not too many. So so all of you who've read Lute Kapol's second edition to Introduction to Multivariate Time Series Analysis, I think the first edition, I think it was like on page 106. There was one of the longest equations. No, the longest equation I've ever seen in a book was in college. I was a physics major, and for some reason I was reading this book on laser physics, and there was an equation that lasted 4 pages. But in this Lute Kapol book, there's actually equations that last like 2 pages, and they're the equations for the delta method expressions for the impulse response functions. So it's like vec of everything inversed, and then you just go crazy with all of these Kronecker products and everything, and it just goes on and on and on and on. And so that's if you're a believer in asymptotic theory, then what you would say is that those coefficients of the VAR are asymptotically normally distributed, and we're going to take a function of those, which is going to be the transformation from the AR coefficients to the MA coefficients. And that function is continuous, which it is, and it has derivatives, which it does. And so we're going to say that because theta hat is consistent, we're going to be able to approximate this function as a linear function locally, and that says that it's going to be these VAR MA coefficients are going to be asymptotically normally distributed, where the distribution, the variance is going to depend upon the AR coefficient variance, and then the linearized difference between the AR coefficient and the moving average coefficient. And if you believe that, it's true. So this is true. This is a true theorem, and it has almost nothing to do with reality in terms of VARs. So these are not these. Actually, that's probably too strong a statement. There are certainly examples in which these provide good approximations, in which the delta method provides good approximations to impulse response functions. But unfortunately, those examples are really pretty simple ones where you have a small number of VAR parameters and you don't have a great deal of persistence and things like that. What this hinges on is having a large number of observations relative to the parameters, having G being approximately linear in the range of the variation of the data, which an inverse is the inverse is not, and it also requires the original autoregressive coefficients to be well approximated by a normal, which they are in some circumstances, but they're not in other circumstances. And in particular, when the roots of A of L are large, then we know that A hat the VAR coefficients are going to exhibit substantial bias. In fact, it even goes to non-normal distributions as the roots get close to 1. So I have an example that's worked out here, which I will skip, about impulse response functions at long horizons having non-standard distributions. So I'm just going to skip that. But I will refer you to a paper by Pesavento and Rossi that works out some of the particulars of this in a VAR context and then applies that to this long run, one of these long run inference problems. Okay, so let me say a few words about computing impulse responses. I'm going to keep you for a few minutes more, about 5 minutes more. Let me say a few words about computing impulse response functions and confidence intervals for impulse response functions. So despite my sort of not being very polite to the delta method, that is the natural place to start. So in the sense that we've got a series of formulas for an approximating distribution for the impulse response functions, and so one can have those are programmed up in standard software, and so you can just go ahead and use those as a starting point of an approximation. It is the case that in some circumstances they work well, but in a lot of VAR circumstances they don't work very well, so some other methods have been developed. And there's a family of bootstrap methods that have been developed, an original bootstrap developed by Runkle, which was published in the JBES 20 years ago. And then there's some work that was maybe 10 years old by Lutz-Kilian that he did in his thesis, and then subsequent to that, looking at more sophisticated bootstrap algorithms. And there's also some Bayesian methods, a particular Bayesian method, Bayesian Monte Carlo integration, that Sims and Jha proposed in a paper in Econometrics in 1999. Kilian and Chang have a paper in which they do a Monte Carlo simulation comparing these different procedures, and they do it again for a number of different designs that are actually based on real published VARs, which is a very nice feature of it. It's a lot more work to do it, but it's a very nice feature. And here's a plot, if you can see it, of some of the results from the Kilian and Chang Monte Carlo study of the quality of the impulse of the confidence sets for the impulse responses. So, in particular, what we're talking about is a Monte Carlo study where you compute an impulse. You compute an artificial set of data, and then you compute an impulse response function from a VAR, and then you compute confidence intervals for that, And then you do that over Monte Carlo repetitions, and you find out what fraction of those confidence intervals contain the true impulse response function. And since it's a Monte Carlo experiment, I know the true impulse response function, and you can see what fraction contain it. And I should make an additional point, is we're not talking about impulse response functions. We're actually talking about it coverage at a point. So everything here is point-wise. So we're not talking about containing the entire path. We're talking about containing the true impulse response function, say, at the 12-month horizon, which is how all of these intervals are computed. So you can do that for a variety of different methods or algorithms for constructing confidence intervals for impulse responses. And these are the results. Okay, so it is very hard to see this. I'm sorry about that. It's really hard for me even to see this. The dash line. The dash line is this Sims and Jha thing. You can't even see. Here's the deal, okay? I'm going to summarize the results, okay? None of these seem to work great, okay? In fact, all of them, in this one case, so here's a couple of cases where at least we're not going to get too stressed out about it, because the coverage rates start to decline after 30 months. But that's like 10% of the data set. 30 months is reasonably far out. So at least we've got reasonable coverage in these cases in the first 30 months or so. This, it starts to flake out around 2 years. And here, it's entirely flaked out. And so depending upon the procedure, this one happens to be the Runkle bootstrap that's worst. At the 10 or 20 month horizon, the Runkle bootstrap is covering, instead of 95% of the time, it's covering maybe 60% of the time. And these other ones are not covering 95, they're covering maybe 85% of the time, even at very short horizons. So what Killian and Chang, so let me just tell you what they conclude. They do a whole bunch of different things, and the answer is there's no obvious ranking between these in the sense that sometimes one is better, sometimes the other is better. But the one that, the one that Killian likes the best is his own. And so here's the algorithm. Here's the algorithm. And so the algorithm is you compute the VAR estimate, you compute a bias adjustment. So there's here's some more really horrible formulas on the bias. So some of you might be familiar from the finance literature where there's been attempts to bias adjust estimates of like autoregressive coefficients using some formulas from Shaman and Stein. That might ring a bell. This is the multivariate version of it using for VARs, which is this Pope 1990 paper. And so you compute the VAR estimate of the A's, you bias adjust that, you do a bootstrap, and in the context of the bootstrap, you bias adjust everything, and then you construct your confidence intervals from the percentile draws. If you followed all of this and you're a bootstrap aficionado, you would say, why are they using the percentile rather than the percentile t? And that is a great question, and there's no real answer to that question. Okay. So let me make a couple of concluding comments. So I think there's been some pretty interesting developments in identification in SVARs over the last decade or so. I haven't talked about the DSDE stuff. I'll talk about that in a little bit. I think this high frequency is very promising. I mean, the thing about the high frequency and the natural experiment ideas is that you're saying, let's try to get new data to bring to bear on this problem. And I think that's got to be a good instinct. This sign restriction idea is quite interesting. It raises some subtle inferential issues that have not been fully worked out. The heteroscedasticity technique is plausible. There might be some plausible applications of that. The big assumption of the heteroscedasticity technique is that the R's are not changing, but the sigmas are. If there's a situation in which that's plausibly the case based on institutional or economic knowledge, then that's a method that one would, I think, feel comfortable using. There are a number of inferential issues that come up. There's this set identification issue that has come up a couple of times. There's these issues with inference with long-run restrictions, which I think in light of yesterday's talk could be viewed as weak instrument problem, or in light of tomorrow morning's talk could be viewed as a hack estimation problem. And then there's, I think, an unsolved problem about what the best way to produce confidence bands is for impulse response functions. There's some interesting new work that, in fact, some of it was just presented last week at the Summer Institute, but I think all of that, none of that is really ready for prime time. And this is, I think there's methods that are plausible right now, like this Killian bootstrap over bootstrap or bias-adjusted bootstrap. But that, as a matter of theory, doesn't work and cannot work when those things are highly persistent. And I think there's more interesting work to be done on that. Although I guess as practical advice, I think using a suitable or an appropriate bootstrap is a pretty reasonable way of proceeding under our current state of knowledge. So that's where we are for this, and we're going to have to start again a little over 20 minutes. I'm sorry about that for the DSGEs.